Okay, in section 5.5, the title of this section is called Multiple Angle and Product to Sum Formulas. We're just going to do the multiple angle formulas because the product to sum formulas I rarely see in calculus. So the multiple angles you do. So that's why I want to focus our concentration there. So first, there's three formulas up at the top called the double angle formulas. And the next three examples say prove that those formulas actually hold. Okay, so the first one says prove the double angle formula for sine. Okay, so we want to show sine of 2a is 2 sine a cosine a. So we want to prove this is an identity. And again, what does an identity mean? If I pick your favorite angle in degrees or radians and put it here and here and here, that will equal that. Okay? Okay, so let's prove this is true. So remember from section 5.2, how do you prove an identity? You start on one side and work your way to the other. Okay, so this is what I'm trying to show. Right? I'm not solving an equation. I'm not doing things to both sides. Remember, in an identity, I don't know the sides are equal. When you know two sides of an equation are equal, if you do the same thing to both sides, you get a new equation that's true. I don't know that these are equal. Okay, so I'm going to start on the left. Again, write down the side you're starting on so the reader knows which side you're starting on. Okay, now I'm going to rewrite this 2a as sine of a plus a, right? A plus a is 2a, no problem. Now, why did I do that? Because now I have sine of a sum of two angles. And in the last section, we learned the addition formulas for sine and cosine and tangent, right? Remember, we did sine of a plus b, but we're doing that, but a and b are the same thing now. Okay, so what was sine of a plus b? Okay, that was sine a cosine b, but b here is also a, plus cosine a sine b, which is also a. Right, so I'm using the formula from the previous section, in section 5.4, right? So sine of a plus b is sine of a cosine b plus cosine a sine b. Right? So a and b are the same thing here. But notice I have sine a cosine a plus cosine a sine a. Multiplication is commutative, so this is the same thing as sine a cosine a. So you have a sine a cosine a plus another sine a cosine a is 2 sine a cosine a. Done. So this is a special case of the formula in the previous section. A and b are just both a. Okay? So you've used this formula before, you just didn't know it. Okay? So sine of 2a is 2 sine a cosine a, and that's that one. Okay, the next one says do the same thing with tangent. Okay, so let's prove the double angle formula for tangent. So let's look at tangent of 2a. Well, it shouldn't surprise you. I'm going to rewrite 2a as a plus a, just like I did with the sine. And in the previous section, we learned the formula for tan of a plus b, right? Now, what was that? It was tangent a plus tangent b, which here is also a, over 1 minus tangent a, tangent b, which is also a. All right, so I'm using the tan of a plus b formula, but everywhere there was a b, I just replaced it with a. Now let's simplify. Well, tangent a plus tangent a is 2 tangent a. And tangent a times tangent a is tangent squared a. And that's the formula given in this section. Okay, so no problem. Let me write that one up here so we can see it. Tan of 2a is 2 tan a over 1 minus tan squared a. Now you might be tempted to think, oh wait, look at this expression I have for tan 2a. In the denominator I have 1 minus tan squared a. There's a 1, there's a tan squared. Remember we had a Pythagorean identity that had a 1 in it and a tan squared. Could we simplify that? No, the problem is it was, in the Pythagorean identity, it's 1 plus tangent squared a is secant squared a, so you can't really do anything with that. Okay, the last one, they want us to prove the double angle formulas for cosine. Now notice with cosine, there are 3 things that are equal to cosine 2a. So let me start with cosine 2a. do the same procedure, rewrite 2a as a plus a, and go back to the previous section. What was cosine of a plus b? It was cosine a, cosine b, which is also a, minus sine a, sine b, which is also a. Remember, with the sine of a plus b had sine, cosine, cosine, sine. The cosine ones had cosine, cosine, sine, sine. Okay? Well, let's simplify. Cosine a times cosine a is cosine squared a, and sine a times sine a is sine squared a. Okay? So notice if you look at the top under the theorem that says double angle formulas, that's the first part. Cosine 2a is cosine squared a minus sine squared a. Okay? So that's the first part. But it's equal to two other things, so I'm going to continue on from here to try to get the other two. So right now we have cosine 2a is that. So that was the first formula that's given. Notice of the three formulas given for the double angle formula for cosine, one of them has a cosine squared and a sine squared. One of them just has a cosine squared, and the last one just has a sine squared. Okay, so this is the mix. Now let's try to get the next one which just has cosine squared in it. Well, if the next one has cosine squared, I probably don't want to touch this one, but you want to get rid of the sine squared. Well, remember, we've done this before. If you use the Pythagorean identity, remember, sine, let me do the scratch work. Sine squared a plus cosine squared a is 1. So sine squared a is 1 minus cosine squared a. We've used that several times already. So that's how you turn sine squareds into cosine squared. So I'm going to replace sine squared a here with 1 minus cosine squared a. Because those are equal, right? This is an identity we already know. Sine squared a is 1 minus cosine squared a. Comes from that Pythagorean identity. So replace sine squared a with 1 minus cosine squared a. Let's simplify. Notice when I distribute the negative here, I get a minus 1, no problem. But I get a plus cosine squared a. I already have a cosine squared a here, so you add those together, you get 2 cosine squared a. And notice that is the next one in the theorem. So this is equal to this is equal to this. Okay? Now the last one just has sine squareds in it, so if I continue from here, we can do the same game we did here. If you subtract sine squared from both sides, you'll get cosine squared a is 1 minus sine squared a. So I can replace this cosine squared a with 1 minus sine squared a. Right? Cosine squared a is 1 minus sine squared a. Sine squared a is 1 minus cosine squared a. So if we simplify this, notice if I distribute, I'll get a 2 minus the 1, that's a 1, and then distribute the 2 minus 2 sine squared a. And that's the last one. So cosine 2a is equal to this, and this, and this. Okay, so let me write these up here so I'll have them. Cosine of 2a is cosine squared a minus sine squared a, which is equal to 2 cosine squared a minus 1, which is 1 minus 2 sine squared a. Right? So we've verified all three of these identities, but they all come, well, this one, and that first one comes from the sum of difference identities in the previous section, and then these two you get from this one because of the Pythagorean identity. Okay? So those are identities. I'm just trying to convince you where they come from. So we have these we can use. So the next example says, suppose cosine of 2x was equal to 0.3. And the question says, what is 2 sine squared x? Okay, interesting. So they tell us about one thing, cosine 2x, and they want to know about something that looks completely different. Well, obviously, if they give you this value and they want to know this value, there must be a relationship between them. Okay? Now, do we have something relating cosine 2x and 2 sine squared x? Well, here's cosine 2a, and notice that this expression is part of this. Right? So that's the game you play in this section. When they tell you about one thing and want to know about something else, and the two expressions show up in an identity, find the identity that relates the two. So let me write down that one. I'm using the cosine 2a and the 1 minus 2 sine squared. Okay, so I'm going to use x's though. So cosine 2x is 1 minus 2 sine squared x, right? I'm using this is equal to this, right? Cosine of 2x is 1 minus 2 sine squared x. Oops, I said use x and then I wrote an a, x. Okay, well, we know cosine 2x is 0.3. Now be careful. X is not 0.3. I know everybody loves plugging things in for x. It doesn't say x is 0.3. It says cosine 2x. This whole thing is 0.3. Okay, it didn't say x was 0.3. It said the whole thing, cosine 2x. I don't know what x is. I don't know what the angle is here. Okay, and notice it doesn't say find the angle. It doesn't say find x. So what are we trying to find? We're trying to find that which is right there. So we need to get that by itself. Well, subtract 1 from both sides. 0.3 minus 1 is negative 0.7. Right? So I subtracted 1 from both sides. That just left negative 2 sine squared. Now I know what you really want to do here. You really want to divide both sides by negative 2. But be careful. The problem asks for 2 sine squared. So you want to leave the 2. Now you don't want the negative. If you multiply or divide both sides by negative 1, you get 0.7 is 2 sine squared x. And that's what they wanted, 2 sine squared x. So there's your answer, is 0.7. Okay, so you don't know, I didn't want to say, you're not trying to solve for x. It didn't say find x, it said find 2 sine squared x. I have no idea what x is, but 2 sine squared x is 0.7. All right, so do you see the game here? They told us one value, they want to know another value. What identity relates those two? Okay, so there's x and 2x, and it's here and here, these two. Okay. Okay, now before we get to the next examples, let's talk about what these identities do for us. We prove them, and I've used them as one example here. Right? What do these identities do? Okay, so sine of 2a is equal to 2 sine a cosine a. Okay, so what this does for you is, suppose you know a lot about angle A, you know, the sine, the cosine, what quadrant it's in, you know, just various information. But you don't know anything about the angle double 2A. Okay? Well, if a problem asks you to find sine of 2A and you knew nothing about the angle 2A, this is equal to this. So to answer this question about 2A, sine of 2A, you could rewrite this in terms of A, and then maybe you know a lot about A. Okay? So you're rewriting this question, I want to know sine of 2A, rewrite it this way, and then you can use information about A. Okay? And vice versa. It could be you don't know anything about A for some reason, but you know a lot about 2A. So if you were asked to find this, you could rewrite it like this, and then maybe be able to work with that. So if you can't work with this for some reason, rewrite it this way, and maybe you can use this. If you can't use this for some reason, rewrite it this way, and then maybe you can use that. And same for the others. Okay? Okay, so also I want you to realize, right, just because there's a 2a here doesn't mean every problem has a 2. Okay? The way to think about these double angle formulas is, if you have an expression like this, whatever angle is here, those have to match, right? Those have to match, those have to match. Whatever's here and here, double it goes there. If you're starting with this side and you're going to this side, whatever angle is here, half goes here and half goes there. Okay, so it doesn't have to be a 2 here is what I'm getting. It doesn't just have to be A here. This A stands for anything, right? Whatever's here and here, assuming they match, 2 sine of the stuff, cosine of the stuff, that's sine of double the stuff. Same thing here, right? Whatever's here and here, if you have this expression, whatever's here and here, if they match, which they need to, that's equal to tangent of double whatever that is. Okay, and same thing for that. So I listed lots of examples here. It's overkill, I know, but I want you to get a feeling that you don't have to have an A and a 2A. Okay? So, for example, let's look at this first thing. Sine of 4x. I want to rewrite that another way. Notice sine of 4x looks like this. It's sine of something. Okay? So, over here, it's 2 sine of something, cosine of something. Now what angle is going to go here and here to make this true? Okay, remember what I said, whatever is here, half goes here and half goes here, right? That's what that means, right? This 2a is double that. So if you know these a's, double it goes here. If you know that, half goes here. So what angle goes here? 4x is this, so this is a 2x and a 2x. So it doesn't have to be a 2 here. What's really going on here, this is sine of 2 times 2x. So a is 2x, so that's the a and the a. But I just, that's so complicated, right? Just whatever angle's here, if you rewrite this in this form, half of this angle goes here and half goes there. Now let's do another example. Cosine of 10y. Okay? So I'm treating this as this, cosine 2a. Now you could pick any one of these you want. Let's just use the first one. I'm trying to illustrate how the angles work, right? Okay. So if this is equal to cosine squared something minus sine squared of something, the same something. Now what angle is going to go here and here to make this true, right? Whatever's here, 2a, a goes here and here, half goes here and half goes here. So instead of 10y, when I go this side, it's 5y and 5y, right? Because whatever angle's here and here, double it goes here. 5y, 5y, double 5y is 10y. Okay? The next one says tangent of 5 theta. See, this one in particular is where students get hung up because notice 4 was even and 10 was even. Now, just because 5 is odd doesn't mean we can't do the problem, right? I'm using the double angle formula for tangent. Again, whatever angle's here, if you rewrite it this way, let me go ahead and start that. 2 tan of something over 1 minus tangent squared of something. Now, what angle goes here and here to make this a true statement? Whatever angle's here, 2a, half goes there and half goes there. Now, what's half of 5 theta? Well, it's 5 theta over 2. Right? It doesn't have to be an even number that divides evenly. Okay? Well, the next one says 1 minus 2 sine squared of 7c. Okay? Now, what does this look like? This looks like this. Right? So the implication is we want to rewrite it this way. I'm practicing going from here to here and from here to here. Okay? So this one looks like this. So if I want to rewrite it in this form, it's cosine of something. Now, what angle do I put there in the blank to make it a true statement? Well, if you have something that looks like this and you have angle A, when you rewrite it this way, what angle goes here? Double the A. So that's double 7c, which is 14c. Right? So if you're going from this side to this side, you're taking half the angle. If you go this side to this side, you're doubling the angle. The next one says 2 sine of 8q minus 3 cosine of 8q minus 3. Okay? So I want to rewrite that another way. What does this look like? This looks like this. 2 sine of something cosine of something. Right? And those are the same thing. They have to be the same, a and a. So by this identity, something of that form can be written like this, sine of something else. So this is sine of some angle. Now what angle goes there? If you have a and a here, double the angle goes here. So double 8q minus 3 is 16q minus 6. Okay, 2 more. Hopefully this is overkill and you say, goodness gracious, why are you doing so many examples? This is so easy. I hope that's what you're saying. Okay, the next one, gosh, look at this next one. 2 tan of 11x squared plus 3x minus 6 over 1 minus tangent squared of 11x squared plus 3x minus 6. Now, what does that look like? That looks like this, right? 2 tan of something over 1 minus tan squared of the same something. Well, this looks like this, which means we can rewrite it this way. Tan of something else. Now, what angle needs to go here to make this a true statement? Well, if anything of this form, you can rewrite in this form. Whatever angle's here and here, it's equal to tangent of double the angle. So all we have to do is double the angle. So that's 22x squared plus 6x minus 12. So these are equal to one another because those are equal. Okay? And then one more of this type. Cosine squared of secant of 9 beta minus sine squared of secant of 9 beta. Wow. Okay, there's a lot going on here too. Now what does this look like? It's cosine squared of something minus sine squared of something. The somethings are the same. Now what does that look like? It looks like this one right here. So what's A? A is secant 9b. Remember, the A doesn't have to be something simple like A or X or 7c even. It could be something complicated like AQ minus 3 or what we had before. So the angle here is this. Okay? So if we want to rewrite that in this form, I mean, you could go from here to here, here to here, but we're practicing going from the double to the single. Okay? By this is equal to this, so it's cosine of something. Now, what does the something have to be? Whatever the stuff was here or here in the circles, double it goes here. So it's cosine of 2 secant 9 beta. Okay? So I made this one weird because it doesn't matter what the A is. Whatever it is, double it goes here. There we go. Okay? So I'll finish the rest of it in a separate video.